diffusion, Brownian, right? Recall that we defined the distance between the centers of two spheres, and the collision radius is the distance between centers of colliding spheres. So that the collision radius is or the collision sphere, I should say, is a surface that has this 2 times the radius of the individual spheres. Remember this at the very beginning. Then we integrated the differential equation for the distribution of the spheres, the number at distance r, and the derivative of that with respect to r. Then you differentiate that and you arrive at this. Then we said the diffusion, that the motion toward all these particles can be described by a fixed diffusion relationship, where this is the collisions per second. That's the surface of the sphere, the area of the surface of the sphere, times the diffusion coefficient times the concentration gradient, right, which we found here. So if we substitute this for dn dr, then we have here this relationship, and we can cancel out the 2 of the RS's, leaving let's see, we have to multiply this by n to get the total number of collision reduction, and divide the 4 by 2 here. Then our next step was to substitute for D the Einstein-Stokes relationship, which is the thermal energy, the average thermal energy, divided by the drag on the diffusing sphere. Now the drag on the diffusing sphere is 6 pi eta times the radius of the sphere, and the radius of the sphere here is half the collision radius, right? So if we substitute this now in here, then we have minus dn dt is equal to 2. Oh, we can cancel out, well, here, we better put it all in here, 2 pi times kt over 6 pi eta r sub s over 2 times n squared. That leaves 6 pi 8 over 2. I better put it all in there. Two pi times and this is squared times r sub s. No, I had it right. Times n. There's an n0. Times n0. I'll square it here. Squared. So that we have this cancels, and we have 2, and this is what makes this 1/3. So we have minus dn dt is equals to 2/3, and the pi's cancel. Kt over eta times n0 squared. And I put a sticking factor on there that ranges from 0 to 1 to when we talked about the decrease in numbers in there. So the number here is 2. Now it gets a little more complicated when you consider spheres of different sizes. But this is essentially what you're asking.
What is the range of application of this formula? I mean, the concentration
What is the what?
For what concentration this formula holds?
What conclusion?
What range of concentration?
Oh, range of concentration?
Yeah.
Well, you brought that up the other day. Remember I pointed out that Brownian motion is rotary in nature. That is, the particles rotate as well as translate. So that you use the longer dimension for the collision radius, and you really should use the smaller dimension for this one. Clay particles are platy, remember? They're not spheres. They're not actually spheres. So that the particles, the volume of the particles is much smaller for a given collision radius than the volume of a sphere. That's what you were considering. They're like sheets of mica. Remember I passed that sheet of mica around? So that if you envision those, they're colliding with each other and leaving space open. So it's good up to the point where they're all sticking, up to the point where you have a continuing mass of connected particles. Now, let's go back to the idea of spheres. Suppose that you have particles, all spheres. This says that particles of any size, down here there's no R in this, particles of any size should move by Brownian motion. The problem is you can't get particles of any size to move very far. That is, when they get bigger and bigger, they're still subject to Brownian motion, still subject to this bombardment, but the motion becomes very much smaller because of this ratio. Here.
Is there another limitation? I mean, is there a limitation at the other end? I mean, the lower concentration.
At lower concentrations, the rate gets very slow. For the example I gave you was for a 1 micron particle, that is 1 micron in length particle. The collisions are about, it takes about 10 to the 12th particles per cubic centimeter. That's a lot of particles, 10 to the 12th. That's 1 with 12 zeros after particles per cubic centimeter to have one collision on a particle per second. Now you can say, well, how about 1 per hour, Typically, Brownian motion is important for very small particles, much smaller than is important in terms of rapid collisions. For very small particles like gold salt, where it's maybe 1/10 of a micron in diameter. In fact, it's the only one that's really important at those dimensions. Any more questions about this? At our last hour, we were talking about deposition, and I'd like to conclude that before going on to the sediment bed. I brought along a paper that's a more recent review of the data that we've been discussing that was presented at a workshop earlier this year. It's a little more concise than the material in the book and has a little bit of new material in it. On page 45 of your syllabus, there's a plot that is a little bit revealing on the process of deposition. Recall we said that at the bed there's a viscous layer whose average thickness might be something like this. and that particles, the velocity gradient in this layer is high. In fact, the velocity gradient in this region is the highest anywhere in the flow, in open channel flow. And that particles may be broken up into smaller particles and carried back up, and that larger particles are settling into this. The small ones are broken up, reform above, and settle back into this. I also said earlier that the particles that arrive at the bed may or may not stick, depending on the shear stress, and that if they don't stick, they either leave a portion of themselves on the surface of the bed or tear up some of the bed with them and are carried back up into this viscous layer. So you can see this is a region of a lot of activity. This is where the aggregation and disaggregation, this region near the bed, occurs in a simple open channel flow. There was a group in Florida whose work I'll describe in a few minutes, whose experiments indicated that there was not an interchange with the bed. And it was later work. And we had some long discussions about this. This experiment was designed to show whether or not there's interchange with the bed. And the way it was done was to put material in suspension in a flume, then decrease at high velocities flow, then decrease the velocity of flow, and let deposition begin. And the concentrations were below about 300 milligrams per liter, so it was settling velocities were constant, and you'd expect it to follow a semi-logarithmic concentration time relation. Then we added to that a small amount of sediment to which had been attached radioactive gold 198. This material, gold, is reduced on the surface of the clay mineral particles and actually becomes a part of the particles. So it makes a very good tracer. It's the clay, which behaves as clays do, and it's tagged with this radioactive gold. We use gold because it's not toxic, not known to be required by any organism, and at the time it was low, surprisingly. The reason it was lowest cost was that it has a large cross section. So when you put it in a neutron field, a lot of the neutrons are caught by the gold, and the transfer is very efficient. I'll tell you some stories about that subsequently. But in any case, we added to added to the flow after the deposition had begun a little bit of this material, and then measured the concentration of gold and of the suspended solids at the same time. And the resulting plot shows that the material labeled with the gold deposited more rapidly than did the material with than all of the material did together, which indicates that since there was lots of material on the bed, the amount of gold added was like 10 grams or something, very small amount of material. A lot of material on the bed. The fact that the gold deposited rapidly just indicated that it was depositing and that the material brought back up from the bed diluted it, continually diluted it. This these data really added fuel to the question about whether there's interchange with the bed or not. And now I think it's generally understood that there is interchange with the bed, and that this area is an area of breakup, or it could be an aggregation of particles if the velocity gradient is really low, and that when there is a breakup, the particles re-aggregate in the lower velocity gradients immediately above this region. Now let me tell you why the skeleton, or the matrix, crushes the particles at lower elevation. So if we have a bed that's formed of aggregates settling on one another, the aggregates at increasing depth experience the pressure of the weight of the particles above them, so that at some point they'll begin to collapse. And of course, when they collapse, that means more contacts per particle, which means that the bed is stronger. So you'd expect it to become stronger with depth. If you look back at the rheological report on page 77, 78, there's a discussion of this crushing, and I'll run through this right quick so that you have a measure of it. We can say that the downward force, I'll call it sigma 1, according to geotechnical procedures, is equal to the volume fraction of the particles divided by the volume fraction of the aggregates. I'll call it P and A, times rho P minus rho L, G times H, and I'll call this H the distance into the bed. Sorry, height of the bed. And from our earlier discussion, we have Vp over Vp and A is equal to 2.5 divided by rho P times Kn, where Kn is the slope of eta over eta L. Remember this is Kn. So then we can write sigma 1 from this up above is equal to 2.5 times rho P minus rho L GH divided by rho P Kn, K sub n. For cohesive material, we can write sigma 1 is equal to sigma 3 plus 2 tau. This is Moore's, comes from Moore's circle. You may remember that from your soil mechanics. And from Poisson's ratio, leads to sigma 3 is equal to K, capital K sub S times sigma 1, where this is called the hydrostatic pressure ratio. The idea is that in a unit cell of material, if the material can deform, then sigma 3 reflects the deformation of this material. So K sub S is pretty close to 1. For a very soft material, and then of course it's smaller if the material is Get this out of your way.
I had a question on the subscripts on that. The values where you're indicating what the slope is. You have a diagram log of eta.
Right. Remember that's our viscometer data?
Yeah, I just can't.
I just wanted to say, remind you where K sub n comes from.
Remind me what the subscripts are. I can't see them from here. On eta.
Oh, yeah, I'll draw it over here. Recall in our viscosity studies, we had the concentration and log eta sub d divided by eta sub L. This is 1.0 here, and this is 0 concentration. And for each order of aggregation, we had a semi-log plot, and K sub n is the slope of that plot.
Thank you.
But if we combine, I lost track of where I was now. If we combine these, then we have sigma 1 equals 2 tau divided by 1 minus K sub s. And substituting that back up in this relationship, that leads to H, in solving for H, equals 2 rho sub p K sub n tau sub b, where this is H of crushing, of failure. Tau sub b divided by 2.5 times 1 minus K sub s times rho p minus rho L G. What I did was to substitute this back into this relationship, and then say, solve for H, and say that the height of where it crushes is the height where it fails, using tau sub b, the Bingham shear strength for the tau. And yeah, that's the only change for tau, and that'll give us the depth for crushing. From the flume data, we found, measuring the depth of crushing, and I'll show you that in just a minute, we found that K sub s is about 0.93. Thanks. On page 71 of your handout is a picture of a device that a penetrometer that was made to investigate the depth of crushing. This is simply a hoop with a screen on it, placed a quarter-inch, having a quarter-inch mesh. And the idea was to see whether there's a change in the structure of the material with depth. We needed something that was sensitive because it's very soft material, and that would also measure it at a short range of depth. That is, it would be sensitive to changes with depth. And you can see that the material acted like butter. You know, that there was the material, the screen actually penetrated it and left little columns of mud. The results of those measurements are shown, and what we measured was the force necessary push the penetrometer into the mud. We did that with a laboratory balance, triple beam balance, mounted on a support so that we could lower the balance and determine the force as a function of depth. If you'll notice, there are a lot of curves on page 72 that have kinks in them, or knees if you like. And if you look at the time, it was done at two places along the flume, 40 feet and 60 feet along a 100-foot flume. And the time is indicated in the legend. The little pluses and circles are at 8 hours. And if you notice, that's the bottom curve. The material was weakest at that point, and the knee occurred at about 2 centimeters above the bottom. Very thin layer. 2 centimeters, a little bit less than an inch. Then at 24 hours, the next curve, and you can see that the knee is a little bit higher, and that the and that the curves are both higher, and so on. If you look at the rest, until finally up above the knee disappears. Now there's two things that are happening there. One is the crushing that we just discussed, and the other is that the material is gelling. That is, it's changing its structure so that it's a more uniform structure, but still one that falls off linearly. On the next page, there's some more plots for later, much later times, and you can see there's no knee, no bend in those curves. So we have two phenomena. One is the gelling, and the H, substituting the elevation of that knee, the bend in the curve for H, and solving for K sub S gives us K sub S equals 0.93, a very reasonable number. So at least in the early stages of deposition, the material crushes completely at some point. Now this argument, this data, supports the argument or the description of structures as being aggregates of aggregates, because the larger pores would crush first, and the smaller ones would crush later. So it looks like this bed, at least when it first deposits, is a collection of aggregates, as we discussed earlier. Now what about the gelling? I'm going to digress quite a bit and talk about gelling because that is important. Let's see, we put here's our bottle, and you can see it's been in there now a week, right? A week and a couple of days, so that's 9 days. You can see it's not quite as thin as it was, or you may not see that, but you can tell by the algae on the side that grew where there was light that it's a little bit thicker than it was, so it hasn't consolidated as much as it would. And if you wiggle it a little bit, you can see there's a little bit of flexibility, but still you can tilt it. It has much more strength than it had as a fluid, and you can see somehow it's pretty strong. It's there. It's beginning to yield a little bit. And if I jiggle it, you can see it jiggles like Jell-O. I'll pass it around, and you all jiggle it and see if you can do it without suspending it more. It is actually a gel, and it continues to gel like that for about 10 days. Well, actually, it continues indefinitely, but most of it takes place in the first 10 days.
What's the definition of a gel?
It's a solid with it's a very weak solid that won't change its volume easily. That is, it's let's see. Probably the better description is that you can make it up out of a powder of some kind with a liquid, and it forms up. And the solid is not very strong, and it has some peculiar properties. One is thixotropic. Thixotropy is a property of a solid, of a gel, that makes it act like a solid until it's sheared, and then it becomes a fluid. And if you let it stand a while, it becomes a solid again. And it's also subject to syneresis. And that syneresis is a change in the structure that tends to shrink it. If you take a core sample of estuarial mud, that is, press a glass, let's say a glass tube into the mud, and fill the whole thing up with water and put stoppers in it, and then put it in the dark someplace so algae doesn't grow in it. What you'll find is that the mud loses volume and leaves cracks in it. These are structural changes in the material, but the most important one for our concern is thixotropy, because since the mud is just deposited, you don't see any evidence of syneresis. It just, if it collapses a little bit, it just collapses. But the thixotropy is quite apparent. If you use a clamshell for dredging, clamshell is just a big two jaws that you drop down like this and close in the mud, and then lift the mud up like this, and then take it over and set it on a bank or in a scour or something like that. When you set it down, it retains its solid. It still looks like a big lump of something, muddy, but still a big lump of something. If you pump it up through a pipe as a suction dredge, the material that comes out is a slurry, and it just flows. You know, water is added to it for sure, but it loses its strength. We put during the construction of the bark tube, you know, that goes from Oakland to San Francisco, there was 4 million cubic yards of material to dispose of that. They dug a big trench, then carried the sections, 200-foot long sections of tunnel out, and placed them in the trench, then ballasted them with rock on top. When they did the job, it was called Transbay Constructors. Did the job. It's a consortium of Raymond Concrete Pile and outfit from Boise and one other, I forgot now. But anyway, when they bid the job, they planned to excavate the material and place it right beside the ditch. You know, they had no reason to take it anywhere. And then put the tunnel in the ditch and ballast it with rock and just leave the material on the side. But the Bay Conservation and Development Commission said that, and the Regional Water Quality Control Board said no, they had to take it out to sea. Well, you can imagine that the extra cost of that really bit into their cost of construction. And so we devised a procedure whereby the material could be deposited about a mile off seal rock, and convinced the Water Quality Control Board that that would be all right, you know, that it wouldn't cause any harm, and the Corps of Engineers and the Bay Conservation and Development Commission. And our argument was that we would assure that it didn't cause a problem by getting background surveys of the beaches. They were worried about mud on the beach, and then taking photographs of the muddiness of the water, turbidity of the water, the other objection of the whole thing, and devising a procedure whereby the water wasn't, you know, there was no apparent evidence of turbidity, and the beaches were clean, and that we'd continue to monitor it until the project was finished, and if at any time it caused a problem, we'd go further out. And we did that. Oh, we also had divers go down and look at the bottom there. The bottom is sand, and it's in considerable motion. Look at the bottom, and they did that at several times during the progress of the project. Now, of course, there was no mud on the beaches. Beaches are sand because mud can't stay there. You know, you wouldn't expect any mud on the beaches. All of the people did. We took aerial photographs of the barge dumping the material. The barge, they used a clamshell to excavate it and put it in a barge, and the barge went out off Seal Rock, out through the Golden Gate. And the barge had it was a bottom dump barge. It had doors that opened like this. And as long as the barge itself was kept clean, and the tug pulled the barge in a straight line out, the material was much denser than the water, and it would go down. There was a trace of turbidity on the surface, but in 20 minutes you couldn't see anything relative to the surrounding. So we took a lot of aerial photographs and demonstrated that. Well, what this is all leading up to saying is that a long time after the project was finished, you could go out there and still see those lumps of sediment on the bottom, even though the whole area was sand because the fines couldn't reside there. These lumps were strong enough. The gel was strong enough so that they stayed on the bottom. They're long gone now, of course, but they lasted quite a long time, indicating that even though the material wouldn't deposit there normally, when it forms a gel, it's stronger, and that will resist intense wave action out there. For you fishermen, that's the potato patch. You know where that is? It's an area of very high wave activity where the bar off the shore. Well, we were successful. That was, when was that? 1970, 74 or something like that. In the last 10 years, EPA has been trying to decide on a place to dump dredge material offshore, and they still haven't decided. They still haven't resolved it. Anyway, thixotropy is one aspect of a gel. Another is that it won't drain by itself. If you put a gel on a filter, the water won't run out of it. It'll retain the water that's in it. Of course, you can dry it, evaporate the water from the surface. Well, let me describe some experiments that reveal aspects of gels that are helpful in determining its characteristic. Professor Day down at Berkeley did an experiment in a soil. This is described in Mitchell's book and other places, where he took a pot and he put in a porous cone. It's called a filter candle. It's used in bacteriology to wash suspensions of bacteria, for example. What it is it's a clay cylinder that's porous, has very, very fine pores about the size of the soil pore. And he connected this to a manometer, a mercury manometer. Where this is mercury and this is water. He saturated the soil and put a cover on it so that there was no evaporation of moisture. And what he found was that if the soil was, say, yellow clay loam from right here, for example, this is saturated soil in here. If you stirred this soil, I'll plot time, and this is H, or I'll call it H, the manometer distance here. If you stirred this soil, the let's call this see, this is tension. That is, it's less than atmospheric pressure when it's like this. So H is negative. If we call if this were the pressure, when you stirred it, it would drop down, and then it would go up sort of exponentially until it was back at this relationship. If at this point you stirred it again, the pressure would fall, and then it would go back up exponentially again, indicating that the soil, after it was stirred and allowed to stand for a while, it was taking water from the porous cone. I'm sorry. The soil was taking water from the porous cone so as to cause this difference, and it did it against a pressure. So the soil was taking up water. Do you follow me? And when you stirred it, it released that water again, and then gradually it would take up water again. Now, this is a curious phenomenon. You know, it's quite an unusual thing. Well, what's happening in there? One thing you can say is that the structure, when you stir it, shear it, you break it up, you make a slurry out of it, and then when you let it stand, it must be making some other kind of a structure that has a larger pore volume, slightly larger pore volume, and it must be able to make that, change that structure against some kind of a pressure. So there's energy involved there. We did another experiment, and I'll show you some slides. Most of this is in your handout, but I think I can explain it better with some slides. We took some glass cylinders. I think they were about 10 centimeters in diameter and about 2 feet long. And they had in them a fritted glass membrane that was fused right into the cylinders. And we connected those to a small 2 millimeter inner diameter piece of glass tubing and put a cap over the top so there wasn't evaporation from the top. And then filled it with salt water. And the first thing we did, of course, was to measure the difference in elevation due to capillary rise on the top. Into these cylinders, we had 3 of them. We put bay mud at 3 different concentrations, and then observed the difference between the elevation of the water here and the difference between the capillary rise, 0 value, and time as a function of time. And what we found was now this is the pressure measured at the bottom of underneath that fritted plate by the manometer on the side. And one of them had 100 grams per liter of material. We suspended this with a plunger just as previously. And of course, for a while, the material was in suspension, and this is logarithmic time in minutes. So for about 15 minutes or so, 20 minutes, the material was in suspension. And of course, the density of the suspension was greater than that in the manometer tube. So the difference, this is centimeters, something over 2 centimeters difference in elevation. But then as the material settled onto the membrane, you'd expect the pressure to decrease, and it did. But then after it settled on the membrane, it decreased more and more until it decreased below the level of the initial level of the manometer when there was just water in there, indicating that the material had deposited, had settled onto the membrane, and that after it deposited and settled on the membrane, it kept taking up water. Another example of Professor Day's experiment. Same thing happened at 50 grams per liter, except as you'd expect, the density was less, and so on. And it also did it. We got a little more data there, and you can see that it stayed below 0 as it went on. And similarly for 19 grams per liter, the pressure went below 0. So what's happening is that the sediment, after it settles, deposits there, it must be rearranging the structure of the particles so that it takes up water. And that's what I want to talk about next. And I'll point this out again, the one we looked at.
Has this occurred without observed swelling?
Well, that's a very small amount of swelling, but we couldn't. The deposit at 100 grams per liter, the deposit was something like this. You have a hard time seeing that amount of swelling. I just want to point out again that there was this change that we attributed to crushing of the aggregates, and that these curves all moved upward, indicating greater strength, greater resistance to penetration, some kind of change in strength with time. Professor Maida's students also observed something like that. This is bed shear stress for erosion, eroding the material as a function of suspension concentration, and they eroded some material to some depth, and then it became more difficult to erode it. And it changed with time. This is 1 day, 1.7 days, and 5.6 days. So he observed gelling also. And he gave the strength of the bed as a this data. You can see that at 1 day, it was much weaker than it was on subsequent days. And this is depth in centimeters, and this is only 1 centimeter, so that you can see that what's happening is happening right close to the surface of the soil. And in fact, gelling continues, but the structure is more open up here. Well, what's happening in the soil that makes that change? There's been a lot of work done on the properties of water near the surface of clays, and I'd like to just describe some aspects of that work. First of all, the water that's near a clay mineral particle is subjected to conditions that it is not in the fluid. One of them is that if we look at the clay particle edgewise, let's say something like this, the water molecules right in the surface, near the surface of the clay, are attracted by van der Waals forces to the clay surface. They're also attracted by hydrogen bonds, which I'll describe in just a minute. The second is the thermal motions of the molecules in the clay surface are much less than the thermal motions out in the fluid. It's a solid. So that means that the atoms in the solid are more strongly held than they are in the liquid. So that there's less thermal activity here than there is out in the bulk liquid. These two processes mean that the particles, that the water molecules next to the surface have less motion, and if there's any kind of a structural arrangement, the structure can grow more easily here than it can out in the fluid. Now, I brought in something, structure of water. So what I'll have to do before going further is talk about water, just water itself. So let's talk about water structure. And no pun intended, but we're really getting off in the deep end when we start talking about water structure. The people have been puzzling over water structure since 1888, so this is nothing new. We have conferences on water structure, and we still are not very close to knowing what water structure is like. The people interested in water structure have formed several groups. There are several camps, and I think each of the persons in those different camps have their own particular views within that camp, and I'll try to describe all these to you just briefly. But let's see why people are concerned about it. In 1888, forgotten the man's name, Anyway, a man noted that water goes through a minimum volume or maximum density at 4 degrees centigrade. So at temperatures below 4 degrees centigrade, increasing the temperature causes it to contract. Negative expansion. At 4 degrees centigrade and above, it expands with increasing temperature. And he said the only way you can possibly explain that kind of a behavior is that there must be some kind of molecules must be connected together in some way so that their modes of vibration are different below 4 degrees than they are above 4 degrees. There must be some kind of a structure. Then, many years later, professor of sanitary engineering in Florida, whose name also escaped me, pointed out that water molecules in ice have a sublimation energy of about 12.2 kilocalories per mole. Sublimation is the evaporation of ice, that is the change from solid to gas without going through a liquid stage. It's about 12, I think it's 12.2 kilocalories per mole of water. But when water melts, it's about 1.44 kilocalories. That's a heat of fusion. So that there must be a lot of energy that's in bonds that are broken when it evaporates that aren't broken when it melts. It must be connected, particles, molecules must be connected to each other. Rodebush was the man who first said that, and he said it must be due to hydrogen bonds. These are relatively weak bonds in the chemical.
What is the 12.2 kcal per mole?
This is heat of sublimation.
What's the rate of evaporation from the water?
It's about 590 calories per gram. Now, 18 times 590, whatever that is. That it changes with temperature. Changes.
I'm wondering how they relate, like going from solid.
It ought to be the difference in these two. Ought to be. I'm not sure that it is. There may be an entropy term in there. But, well, hydrogen bonds turn out to be really important bonds in biological sciences. You know, our DNA has the structure it has, the double helix structure, because it's held that way by hydrogen bond. And the hydrogen bond comes about because the water molecule has S shell electrons in the oxygen atom, S shell and p electrons, p orbitals, and the p orbitals are in this kind of an arrangement, almost a tetrahedral arrangement. P orbital is the one that S orbitals, remember, have roughly a spherical paths, and the p orbitals have paths like this. And there are two of them that come out this way, so that these p orbitals, unpaired electrons, provide sites for covalent bonding. Well, a hydrogen atom has one electron, and it satisfies this unpaired p orbital here, and the other one, hydrogen here, so that we have the nucleus of the hydrogen here and the nucleus of the oxygen in here. That makes this part of the water molecule positive, and these unpaired orbitals on this side are negative, so the water molecule has a negative stripe down its back. Let's look at it from this direction here. If we do, then what we see is a stripe from pole to pole. It looks something like this. It's all negative. So the water molecule then has positive sites where the hydrogen nuclei are, which hydrogen nuclei is infinitesimally small compared to an oxygen atom diameter. So that essentially we have something like a sphere with two positive spots on it and a negative stripe on its back. So you can immediately see that somehow one oxygen plus site can be attracted to another oxygen's negative stripe. And that's called a hydrogen bond. It's an electrostatic attraction of the positive spot on a water molecule to a negative stripe of another water molecule. Now there's also another kind of attraction, and that is the fact that the center of the oxygen atom is negatively charged, so this is a dipole. And you can imagine opposite dipoles having some attraction. But the main one is this hydrogen bond. The energy of the covalent bond here, the OH bond, is about 110 kilocalories per mole. The energy of the hydrogen bond is on the order of 6 or 7 kilocalories per mole. I'll say, you'll read different amounts, 5 to 7 kilocalories per mole. So a hydrogen bond is very much weaker than a covalent bond. It's you don't easily separate the hydrogen's atoms from the water molecule itself, but you can separate water molecules with about 1/20th or 1/15th of the energy that it takes to separate a hydrogen bond. Now in an actual bond, the hydrogen nuclei are much closer to the atom that they're attached to than they are to the nucleus of the other water molecule. It's about 1 angstrom spacing between the center of the nucleus of the water molecule and its hydrogen bonds. And the total here is about 2.8 angstrom spacing. I think this is a good place to stop, and I'll start on Tuesday talking about water, and then we'll get back to why clay is gel. Water is really a fascinating subject, and you can get hooked on it. And you can get into some very involved discussions at conferences on it. I'll try to describe some of those before we're through. We all have a nice weekend. I made it especially nice because there's no homework this weekend. I'll make up for that later.
Sediments.